Okay, so we're going to finish up all of the phase diagrams today, as far as I can tell. That's nothing left, and then we'll do a review and an exam. So I would say for getting ready for the review, I would go through every phase diagram in the notes and make sure you understand these things. What phase is in each solid region of the phase diagram? So all of the solid regions. I'll just look at this next one here. Oh, it's not behaving. Let me cancel this and get back over here. Okay, so like in this particular deal, we've got some regions that are one phase, other regions that are two phase. And so up here, whenever you see like P equals 1 and P equals 2 on these phase diagrams, it's telling you there's two phases in equilibrium or one phase in equilibrium. Sometimes the two phase region is just a single line, like in a PT phase diagram. Those are the familiar shape. Let me draw it over here, where you've got the line, there's a triple point, and then it goes up like that. There it's solid, liquid, gas, and those lines are two phase lines where like solid and liquid are in equilibrium. And then the regions are solid, single phase, solid, liquid, or gas. So just go through every one of them. And really, I need you to bring your questions on Monday, because this is, for me, a recognition thing. So I don't know how I learned it. So on a review, I can't review how to learn it. You have to bring me your questions. So you've got to prep for Monday so that you have all your questions that I can answer then. Yeah. So that's normally the reviews are more passive, right? You show up and then I give you like a refresher on things. But on Monday, it's really going to have to be on you to bring your questions. Excellent. So this is kind of an interesting one. We're getting into solid behavior, and this is a phase diagram for the solid region, and this is hydrogen and palladium. It's a really important piece of metallurgy, and that is anytime you have metal exposed to hydrogen, it can dissolve hydrogen. Like hydrogen can dissolve into the metal. It's really weird, and it can cause embrittlement. And so hydrogen embrittlement is a real issue in industry, because you have, structural metal in particular needs to maintain its metallic properties, its flexibility, its compressive strength, and so on. And if you have too much hydrogen dissolved in the metal, then you can form a very brittle hydride. And so this is just this two-phase region where you have mostly palladium with a little bit of hydrogen, few hydrogen atoms flowing around. Like if you had maybe 10% hydrogen dissolved into palladium, the surface would be very hydrided, and some of that hydrogen had migrated into the bulk of the metal. So you've got a two-phase region. You have that lever rule where you have a fulcrum wherever your overall composition is, and that highly hydrided metal. The x-axis here is the mole fraction of hydrogen. And so that metal can be very brittle. So you can kind of chew into the metal with hydrogen. Now, some of this hydrogen can go through the metal and come out on the other side. And so that's a great way to separate hydrogen, is to have a small window of metal, hydrogen on one side, the hydrogen will percolate through. And that's what they thought they were getting with cold fusion. Do you remember hearing anything about cold fusion? No? Okay, they were doing an electrolysis experiment, and they had a palladium electrode, and the hydrogen ions were going into the palladium and being, getting their electron. And so there was hydrogen atoms in the palladium. And they had the palladium electrode separating the hydrogen from another container, and helium was showing up on the other side. They said they had excess helium in this apparatus. And the only way you would get helium would be from fusion, right? Two hydrogen atoms making a helium. And it was not repeatable. Like other people had, said this was very exciting, because if you could do fusion at room temperature and get the energy out of it, then, problem solved. I mean, we have an endless supply of energy then. This was at the University of Utah, and it was Pons and Fleischmann were the two researchers. There's a couple of things they did wrong. They put out a press release before they put out the peer-reviewed paper. Yeah, and so they're like, look what we did. And then they wrote out the paper, and then people tried to repeat their experiment from the paper, and they couldn't do it. And it spoiled the well for this whole fusion, cold fusion research. And if you go now to the U.S. Patent Office and you file any patent that has anything that seems to smell like cold fusion, it's automatically rejected. So that's sort of the biggest like black eye in terms of getting the press release before the paper. You really need to put your papers out there and have the community kind of vet it and try to repeat it and so on. You're still going to get credit. You're the first one that published it, but the university wants to make a name for themselves and so on. Now, I've always been bothered by this phase diagram. You can see the one in your notes looks a little different. So I tweaked it a little bit last night just to show that I don't exactly understand what goes on in this region of the phase diagram where I drew this cloud, because over here we have 100% hydrogen. So what would it mean to have like hydrogen gas, not even H2, but hydrogen gas, that we have little bits of palladium metal just floating around in the gas phase? This is a solid phase diagram, so maybe we're at a high pressure where this is hydrogen solid and you have palladium dissolved in hydrogen solid. So maybe that's a way to understand it, that we're at high enough pressure that this is all solid. So anyway, I have a big question mark over on the right-hand side of this phase diagram. But over on the left-hand side, we have a little bit of hydrogen dissolving in the metal. If you get too much, you get phase separation, and you have a very brittle metallic surface that's been hydrided. Okay, let's talk about, let's flip back to liquids. So now we're at liquids again. And this one has a lower critical solution temperature. So this is a two-phase region. You see P equals 2 here, and P equals 1. And down below that temperature LC, it's one phase. And so it's miscible down here. And phase separated up here. Now that's a really bizarre situation, right? But again, these are all molecular. You can hopefully find molecular reasons for this behavior. So if you think about this, this is triethylamine. And at low temperatures, these ethyl arms on that amine are not very active. Remember, for our heat capacity, we talked about vibrations being activated at certain temperatures. So above a certain temperature, these arms the twisting motions are going to be more active. And down below, this solution is free to hydrogen bond to water. So this is ethylamine and water. And so you might have this hydrogen bond to water. And the ability for water to associate with this molecule is going to be temperature dependent. So if you raise the temperature, then these arms are scaring off the water. They're sterically hindering the water's approach. And so there's less hydrogen bonding at higher temperatures than there would be at lower temperatures. So this is a really interesting situation. At lower temperatures, we have a miscible situation. You raise the temperature, we have phase separation because those hydrogen bonds are interfered with by the rest of the molecule. So that's pretty neat. I mean, I think. And if you don't think so, I appreciate you not saying it. We had an incident in graduate school. The thermodynamics professor said, "Isn't that cool?" And this person in the front row said, "For you." Yeah. And this was graduate school, and he's like livid, pointing at this person with an eraser, saying, "If this isn't interesting to you, then you must be in the wrong field," right? And he threw the eraser down on the ground. This person went to the chair and said that the professor threw an eraser at them. And the rest of the class went into the chair's office and said, "No, that is not what happened. Let's give you the rest of the context." So I remember that every time I say, "This is so amazing." I think you might be sitting out there going, maybe for you, Look at this one though. The next one's even better. This is nicotine in water. And it has an upper and a lower critical temperature. So there's like a circle in the middle of the liquid phase diagram where you have two layers. And so at low temperatures, it's miscible. At high temperatures, it's miscible. In this middle region, it's not miscible. There's two layers, partially miscible, we would say. And so how can we explain this? Well, think about the high temperatures. At the really high temperatures, and again, this is 210 C, so I mean, it's way above the boiling point of water. So what we have is a pressurized situation. So up here we have, hot temperatures. Hydrogen bonding is less significant at high temperatures, right? Because water's got so much kinetic energy that the hydrogen bonding time is less significant. And so entropy will drive that mixing, and you have, miscibility up here. So at high temperatures, H bonding is less significant. Let's go all the way down to cold temperatures. Notice nicotine has some hydrogen bondable amines. And so at low temperatures, water can hydrogen bond to nicotine and be miscible in all solutions, at all concentrations. And so that weak hydrogen bonding to nicotine allows it to be miscible in this region. But then in the moderate temperatures, the hydrogen bonding to nicotine is disrupted. And so water likes itself more than it likes nicotine in that situation. And so the nicotine layer is just excluded from water. As soon as that hydrogen bond is disrupted by thermal motion in the middle of this chart, then it's sort of like water excludes nicotine and snaps back to itself. And so the nicotine layer just spontaneously separates. So that's this middle region where it's two phases. And this really shows that even though there's two layers, look at this right here. These layers are not pure nicotine and pure water. They're very polluted with each other. So I really hope that you learn from this course. One of the take-home lessons is that when you have a two-phase liquid, they're not two pure phases. That they can have a substantial amount of the other component in them. And so this layer that's mostly nicotine has about 30% water, right? 1 minus 0.7, okay? And then this layer over here is about 60% water, water, and 40% nicotine. This is 70% nicotine. So those are not very pure at all. But the one layer is, nicotine rich, and the other layer is nicotine poor. So those are the craziest liquid phases. Now let's go to where we start to freeze things. We're going to go cool things down and get into the freezing region. And, not yet, sorry. My memory of that. Okay, so here's where we have now boiling. We're going to raise the temperature and boil the solutions. And so we have boiling above a two-phase liquid. So here's the upper critical solution temperature, TUC. So it's miscible here. What is it up here in this region? Looking at this curve, all these curves, what do you think's going on up here? Well, it tells you right there, actually. It's vapor. So it's vapor up here. Down below those lines, it's miscible, one-phase liquid. Down below these lines, it's liquid with two phases. So you've got a layer that's rich in B and a layer that's rich in A. In all of these situations, I have not really emphasized it this year, but anytime you get any kind of graph or chart, go to the axes first, see what's being plotted. So down here, we're plotting mole fraction of B. So over on the right is more B, over on the left is more A. Now this top part is what type of azeotrope. So I see an azeotrope here. That's where that vapor liquid line pinch together. What kind of azeotrope is this? it's a low boiling azeotrope. So those are our classifications for azeotropes: a high boiling azeotrope or a low boiling azeotrope. The azeotrope boiling point is much lower than either of the pure substances. So that's what we call a low boiler. And if you have a low boiling azeotrope, that's what you would collect in the collection flask. So if we were to fractionally distill this, the collection flask would have the azeotrope in it. Now, sometimes the miscibility is so poor that the two-phase liquid, there's no miscible region. So you see here's the liquid region. It comes up and it hits this point. At this point, it's really not an azeotrope. We would call it a eutectic behavior. Okay. How do I know that there's a boiling point there? It's because of the vapor line. So this vapor line right here is this blue line, and you see there's a blue line that comes all the way down to this point. So right there, where that blue line ends, anything above that horizontal line that I've drawn is boiling. Everybody follow that? Yeah. Okay. So I'm going to start here at B3, and I'm going to say, let's boil that solution. When we get here, it's going to boil there. The vapor composition will be this eutectic vapor composition. Okay, but that's still my fulcrum, and my liquid phases are this composition and that composition. So it's my two liquid layers have those two compositions. My vapor has this eutectic composition. Okay. If we were to fractionally distill something, like we had a very pure B, this is a really interesting situation. So we've got a solution that's mostly B, maybe has 5% A in it. B has a high boiling point here. A has a lower boiling point. So I go into the lab, I'm going to try to distill that 5% A out. Makes sense, right? I got 5% A contaminating my B. I want to purify my B. I'm going to distill this and get that A out of there. And this is what happens in that experiment if you have this phase behavior. I heat that solution up, okay? And it boils at this temperature because that 5% A really lowered the boiling point. Now, and then the vapor has this composition. It condenses in the flask, and when I cool it back down to the original temperature, I end up with a two-phase layer that's even more contaminated in B, and then this layer that has a lot of A in it. And so that's like, wait a second, I had a homogeneous solution. I distill this, and I look in my collection flask, and I've got two layers. And one of those layers is rich in A, but it's not pure A, and the other layer is rich in B, but it's actually less pure B. So it's wrecked. The whole thing is wrecked. And so, distilling these partially miscible solutions can really be a mess. So that's really strange. And then when I saw this figure, I always thought that whole region contains two phases, either a vapor phase and a liquid phase, or two layer liquid phases. And to me, that looks really cute, that diagram. I think it looks a lot like a little rabbit. Okay, so so we're getting close to Easter. It kind of bounces around in the spring, but that's my little rabbit diagram. This is a eutectic boiling mixture in the liquid phase. So I've already kind of talked about distillation of these partially miscible liquids. Sometimes, you have a homogeneous solution in the pot. You think you're going to purify it by distilling it. You look in the collection flask, and you have two layers, and it's a big surprise. Okay. Let's start looking at solid liquid phase diagrams. Okay, so how would we know that this is a solid liquid phase diagram and not like a boiling, a vapor liquid? So VLE, vapor liquid equilibrium. How do we know it's not a boiling and vapor diagram, but that it's a solid diagram? What do we see in the liquid vapor equilibrium that we don't see in the solid? So here's a solid phase diagram. Let me go back to a liquid one. Let's look at that one on the left. Ignore this stuff. So if we're just looking at this, let's ignore this for now, okay? So I'm looking at here. This is vapor. This is liquid. All right? Get that in your mind, and then now look at the solid one. If I didn't have anything labeled on this diagram, all I saw was the blue curve, what's missing? The two-phase area, which has that black curve, which is the boiling point curve. So let me go back up here. This one is missing, this guy right there. So we don't have the boiling line. Okay. Essentially, that boiling line has been moved out to the far edges over here as a vertical line. Become. Can you read that? Become. Let me do better. The boiling lines become vertical comp lines, vertical composition lines in the solid liquid phase diagrams. Does that make sense? So let's see how this turns out, because we are in this region where we have two phases, like you said, the two-phase region. In the solid liquid, we definitely have two-phase regions, but it's a little tricky because the second phase is a vertical line in the composition area. So let's look at that. So here's a solid liquid phase diagram. So we're going to start at point A1, and we're going to cool this down. Do y'all have the little pictures in your notes? No, you don't. Okay. You may want to draw these little pictures. So get your artwork ready, your art skills. And so at A1, if we were to look at this under a microscope, it's a liquid. And if we were to color code it, over on the left, that vertical line is pure A. And over on the right is pure B. So notice I've got some colors associated with that. So A is yellow and B is blue. And so if I'm looking at a liquid that's a mixture of a yellow and a blue substance, what color would it be? Green. Yes. Okay, very good. I saw you say it to yourself. All right, so it's kind of it's, compared to the blues, it's green. That's looks a little more green on my screen. So A1, if I looked under the microscope, single phase, look what I have. I have A, liquid, plus B, liquid, at whatever relative concentrations. It looks like it's about 80% B. Make sense? 80% B, but I can't tell the difference. The colors are blended. It's a homogeneous mixture in that region of liquid, A and B. So then when I get to A2, this is a melting point, freezing point line. So at A2, it starts to freeze. So I'm entering a two-phase region, and the lever rule starts to apply. Now, when it first starts to freeze, the lever rule, I'm all the way over to A2. So very little B starts to freeze, but it starts to grow. As I drop the temperature, B starts to crash out. And so here we are at A2. The very first little crystal of B, or little solid region of B, starts to grow at A2. But I still have a lot of A liquid and B liquid. So the liquid phase is still a single phase, but in that liquid phase, I have both substances. I have A and B liquid. So good so far? What do you think happens when I get to point A3? I just have more B precipitating out. So the B is and it's pure B because that's a vertical line. So pure B is crashing out a solution. If I do it slowly, I could grow crystals of B. If I do it fast, I just grow lots of little amorphous solid parts of B. So we're not really saying too much of the perfection of the B phase. We're just saying that it's a solid. And look at the color of the solution. It's a little bit changed, isn't it? It's no longer deep blue. It's starting to show a little bit more yellow because we're crashing out the bluest substance. We're crashing out B. What do you think happens at A4? Look at the liquid equilibrium line. That blue line is the liquid equilibrium line. And so we're going to sit at A4 until everything becomes solid. And that's called the eutectic pause. What are we doing? We're cooling it down. So we're cooling it down, we're cooling it down. B starts to crash out a solution, but it's all very smooth. And then we hit a spot where we're going to sit there and pull heat out of the system until everything is a solid. And from that point below, we have solid A and solid B in equilibrium with each other. So at the eutectic, at A4, we sit there and we keep precipitating out B, and then the A liquid and the B liquid, all of the B is gone eventually, and we just have A left over. So if we get down to A5, then we have distinct phases. We have an A phase and a B phase, both are solid. And I found a micrograph. Like if you were to take metal, cut it, polish it, look at it under a microscope, you would see the different grains, the solid and liquid grains. And here's an example of that. This is a nickel superalloy. You can see the blue grains surrounded by a little bit of yellow. And that's why I chose the colors I chose. I found this micrograph, and then I tried to make this match that micrograph. Okay, so like the nickel is probably the blue, and then what other kinds of like steel composition, the iron and things are acting like a glue that holds it together. So it's a solid glue. You've got grains of one metal surrounded by a glue of another type of metal. And that's really where this is the exit ramp for material science. If this really excites you, then material science may be the place you would like to go next for your next degree, if you wish to do that. We get into how do we make a metal that has this property. It's lightweight. It's really flexible. You could stretch it, but it won't break. You know, the grains can shift if your glue is flexible enough. But if the glue is strong enough, it'll still hold. And so this grain size, grain strength, compressive strength, tensile strength, can all be engineered by these alloys. So when you think about why do they have all these alloys, they all have different properties. And getting in there and figuring out what this metal adds to the alloy versus what this metal adds to the alloy is material science. Any questions on this? Let's look at the temperature curves. So up here, this is the same letters, A1, A2, A3, A4, and A5 from the previous diagram. And these are different, each line is a different composition here. So going this direction is different. different compositions, all the way till we get to the eutectic composition. So that's the one that is liquid the longest. And so that's one way to describe a eutectic mixture. It has the lowest melting point, and it's liquid the longest. It has the lowest melting point, then it's going to go down to lower temperatures and be the lowest freezing or the lowest melting point. That's really important in things like solder. So think about when you're soldering chips and stuff, you don't want to damage the sensitive electronic components. You want to make a metal-to-metal bond. And so you find a particular mixture of metals that melt at really low temperatures. So you can put the soldering iron on there, and you put the metal in contact with it. It'll keep the tip of that soldering iron at that low temperature as long as it's wet with solder. And then you get the leads of the circuit up to that temperature so that the solder will wet the leg of the circuit, chip, and wet the little pad that it's sticking on. And then you pull the iron off and it freezes. And now you've got a metal-metal bond. So that's how soldering works. We use eutectics for solders. You can make really low melting eutectics with lead, but obvious for health reasons for the people doing the soldering, they wanted to get away from lead. So lead-free solder is a really big deal. They put in silver and tin and a bunch of other metals and find those eutectics that have really low melting points. Now look at what we've got here too. We've got over time, we're cooling this down at a particular rate, and notice that the liquid has a different rate of cooling than when B is precipitating. And so these are the different heat capacities. Okay, so we're pulling energy out at a certain rate, so many joules per second, and the energy coming out of a solid is a little different than the energy coming out of a liquid. And so we see this change in slope over time when we start to see B precipitating. And we can use the differential scanning calorimeter to kind of measure some of these things. And so these cooling curves and so on can be used. You can use calorimetry to get those. But right here, as we see this eutectic pause, we see B is precipitating, and then we see this eutectic pause, and then we have the solid cooling. Also, since you think about organic chemistry, and we're doing a melting point to determination to figure 1, the melting point, and 2, to see if it's pure. This is a very impure substance. So if we're reversing this thing, we've got a solid at A5, we start to warm it up. We start to see liquid at A4, but we can still see solid. And we keep heating, and finally that last little bit of solid disappears. We have an enormous range where we have solid, so we know it's impure. Whereas if we have a situation like here, we're right at the eutectic, or at a pure melting point, we would see an abrupt thing. We would warm it up, the solid, and then we would see the sharp melting transition, and then it would be all liquid above that. So eutectics can give you kind of false positives in terms of a melting point, but you would also know it's not pure, because if you're an organic chemist and you're like synthesizing something that you are familiar with and you know the melting point of pure B is way up here. That's Tm for B. And this right here is the melting point for pure A. Thank you, Kathy. And this is the Tm for the eutectic. Y'all understand my little symbols there? So Tm's melting point, and then I have A, B, and eutectic label. Look how much lower that melting point is for the eutectic. So if you had a eutectic mixture of 2 substances in organic chemistry, you'd be really unlikely to make the exact eutectic composition. And you put it in a melting point, and you're expecting, say, 115, and it gets to 85, and it turns liquid, and you're like, oh, what have I made? That's not what I was expecting. So anyway, this eutectic can, in that way, trick you. So it's pretty interesting to me. Now, reacting systems. Sometimes when you put A and B together, they make C. and you can have phase diagrams related to that. So in this case, we have a bunch of different melting points. Now this one is coincidental that the two eutectics have the same melting point. That's not always the case. So I'm going to point to these right here and say coincidence. Okay. Just so that you don't expect that every time. And we'll look at another phase diagram where they're not the same. Now, compound C is obviously AB, right? So this right here is equal to C. C is equal to the compound AB. Okay, and so right here's the melting point of pure B. That's the melting point of C, and this is the melting point of A. Pretty easy. The maximum points are the melting points. And so also, where you're looking at purity in organic chemistry, that highest melting point is what you're after. If you have any impurities in there, it lowers the melting point. We know this from colligative properties. So freezing point depression, that's what this is. So we talk about freezing point depression. If we have a liquid and it's impure, it'll freeze at a lower value. That's what we do with the, trying to remove ice on our bridges. We'll put something down and lower that freezing point and try to keep it liquid so that we don't slide in our vehicles. So we're trying to use colligative properties. Many times they put sand down. They used to use salt, but salt was so rusty on your vehicles, it would promote corrosion. So down here we just dump a lot of sand. Sand will have some components that are soluble in the water, so it will lower the freezing point of water, but mostly it's just to provide grit for the tires. At least that's my understanding. Okay. Notice this third substance has kind of split our phase diagram into two. So if you understand this one right here, then all you do is just double it. That's it. Yeah, so for reacting systems, it's not bad. You get over here and you look at it, it's really just two phase diagrams side by side. Only when you get to this two-phase region where you have two solids, like if you happen to be right here, you draw your tie lines until you hit a vertical wall. And so this phase is in equilibrium with that phase. So at that point right there, you have B solid plus AB solid. See, I don't go all the way to A. I just stop at the vertical line, and that's that composition of the solid that we're looking at. So I think I have some pictures here too. So if the pure A is yellow and pure B is blue, and the part C, pure C is green, then this would be starting at A1, we have A liquid and B liquid. We have no AB liquid. So in this particular phase diagram, there's no way you would have AB parenthesis L. It's kind of interesting. AB by itself was only stable in the solid phase. You warm it up, it melts, the A's and the B's come apart, and you have A liquid and B liquid. Because we don't have any lines above that melting point. The only places we hit on left and right are liquid A and liquid B. So there's no line for liquid C. The liquid C stops at its melting point, and these things split apart and make liquid A and liquid B. Then if we're cooling it down from A1 to A2, then we start to see some C form. So A and B get together, form a solid, and they start to grow. And then we cool it down further at A3, we have more solid C. Cool it down even further, we're at the eutectic on the right side. And then below that, we have B solid in contact with C solid. I'll have to move on. So if you're drawing the pictures, just go from the video. Okay. Now here's some actual experimental diagrams. And this one does have some vertical lines on it. let me just sort of run through this. So we have potassium and sodium, and this is an example where we have this substance called NaC. So sodium and potassium form a compound in the solid phase that's not stable in the liquid phase. It does not have its maximum melting point. It decomposes before it melts. And so that's why they call this incongruent melting. You know, the other melting points are a maximum on the liquid line, and this one is not. So if I'm warming up NaC, Na2K, I get to this point, and it's got enough temperature that it just spontaneously splits apart. Now I go over here and I stop at that phase right there. And then I stop at this phase right here. This is liquid, right? Liquid K, and I'll just do K liquid and Na liquid. And then over here is solid sodium and solid sodium containing, it's a solid sodium containing some potassium. So it's this piece right here, solid sodium containing some potassium is at that point right there. Now, if I find myself in this region right here, I have two phases. It's solid sodium, pure solid sodium, and dirty sodium. Okay, if I'm over here, I've got pure potassium and dirty potassium, two phases. So all of those different phases are labeled for you. Let's look at one that's maybe a little more clear. This is silicon and calcium. Who knew that they could form all these compounds, right? They're only stable in the solid phase. So you would have grains of these different compounds when it's solid. But once you get it above the melting points, then it's just silicon atoms and calcium atoms floating around each other. And here's all your melting points. So this is the melting point here for calcium 1, silicon 1. And this is the melting point for I guess if I don't know how you name these, with dicalcium silicide, who knows? But then this one has incongruent melting. So this one decomposes right there and at 1040 and turns into just calcium and silicon solid, and then the liquid phase. And then this is the melting point for pure silicon, Tm silicon, and this is 842 is the melting point of calcium. So pretty interesting behavior. So this one has like 4 different regions. And so if I dropped you into any one of these regions, just go horizontally and tell me what phases are in equilibrium with each other. And this is still only binary mixtures. So lastly, we have a 3-component phase diagram. So this one I'm not going to require you to like really figure out, but I've gone ahead and shown you at this point right here, that's 20% chromium, 15% iron, and 65% nickel, and it all adds up to 100%. So it's pretty cool stuff, and that's pretty complex. Nickel, chromium, and iron form all of these compounds, and that's where we have stainless steel and all these different kinds of steels and everything. So it gets really complicated, and it's really fun. But if you love this stuff, then you're a material scientist. So get your chemistry degree, don't quit. But you know, you might want to go look at an engineering, like a master's degree or something in material science.